Hi, and thanks for tuning in to the CBA Podcast, a place where we chat about our own recent achievements in the area of electronics, software and mechanical engineering, and more likely than not, give excuses for not having done anything at all. Hello, and welcome back to another episode of the CBA Podcast. Thanks for tuning in. It's been a while, I think 3 or 4 months since the last episode aired, and there are some reasons for that. First of all, I don't record if I don't have anything interesting or at least semi-interesting to talk about. Secondly, I have to have time to do an actual recording because there is some editing going on and simply takes a little bit of time. And last but not least, I have to be in a good mood to do a recording. So every once in a while the planets align, and that's when you hear a new episode. So this is a new episode. So, just for your information, the way I record this episode is a little bit different from the previous times. Usually I recorded one big sound file, just press record and afterwards stop it. And that was 45 minutes, a half an hour or something like that. After which I cut out all the dead pause and all the mistakes and all the weird sounds and stuff like that. Now I do it a little bit differently. I record one small sound file per topic. If it's not okay, I simply re-record it. If it's okay, I, save it, and afterwards I glue together all the little sound files and then remove some dead pause, and that's it. So maybe this is easier, we'll see. Or actually I will see. You will see nothing. And also for your information, this is approximately the 2-year anniversary of this podcast, because I think it started in November 2017, so this is 2 years and 3 months, 4 months, something like that. And I think after the first year we did a little bit of review to see what changed in the first year and how it got where it was. That sounds a little bit more fancy than it actually is. The second year I don't have anything to say. I'd like to say we learned a lot. We didn't learn anything. So let's just keep going. Thanks a lot for downloading it and tuning in. And once again, if you want to send feedback, because we got precious little feedback over the last 2 years, if you want to send feedback, it's always possible. Look at the podcast.cba.si page for an email address, and I'm happy to hear from you. I think in one of the previous episodes I complained a little bit about me not having that much interest in techie stuff anymore. It's probably a phase, and it probably is a phase. I'm starting to look at for example, Commodore 64 demos again. I'm thinking about making my own little thing. Starting to be interested in technology a little bit, so I suppose coming back, it's not a big deal. One semi-related thing, maybe sounds familiar to you, is when I was younger, I remember, for example, programming was easier. Not in a way that was better, but I would just start and do a project. And it was not always successful, but I started more things without really thinking it through. And with electronics and software, this is pretty much what I do for a living now. So for actual paid work, it pays off to make a plan in advance and see if it's viable or not, and see how much it's going to cost in terms of money and time. So I think for hobby projects, maybe there's a fine line between doing that and just starting. But I think I suffer a little bit maybe from what's called analysis paralysis. So thinking it through too much and then seeing all the issues and then deciding not to start at all. So maybe that sounds familiar to you. I think it sounds familiar to some people I know. For example, this is not going to take very long. When I was small, I remember starting a programming project on the Commodore 64. It was a game. And I didn't think it through at all. And eventually the RAM of the computer was full. So no more code would simply fit in the machine. And that was my cue to stop programming. So that was an extreme case, but at least I started it, and I had a lot of fun. It was not a big success, but I had a lot of fun in a way. So maybe that's a little bit more of the way to go for hobby projects for me. Anyway, that's enough intro nonsense. Let's get on to the actual topics. So if you listen to previous episodes of this podcast, at least solo episodes, what I try to do is add some topics about stuff that I took apart or fixed. So that is stuff that I didn't make myself. Secondly, if possible, I would like to include some general knowledge thing, something that I read about or something someone told me about and I found interesting enough to learn a little bit more about. So there's going to be something like that in this episode. And finally, if there is something I would like to tell about stuff that I made from scratch, for example, electronic boards that I made, And maybe if there's upcoming events, I'll usually close with events. So in very early episodes, I would always do a topic list at the start. I'm not going to do that again because topics are not in-depth enough to, you don't need an index for this podcast. It's just turn on, listen for 50 minutes, and then that's it. It's not really going in-depth. So anyway, that's what this episode's going to be about a little bit. In one of the recent episodes, I talked about hot glue to help fastening electronic stuff. Now, recently there was a laptop supply that broke down. There was a cable broken, basically shorting out the output. So I opened it up destructively, and the bare PCB, I fixed it. I added a new cable, or resoldered the cable. Now, I don't want to be zapped by mains voltage when I touch something, me or someone else. So I put it in a plastic box just until I got a new power supply. Drilled 2 holes in the plastic box and stuck the mains and the DC output cable through the holes and fastened the cables and the power supply with hot glue. Now, in the previous episode, or in a recent episode, I talked about depending on your hot glue gun and the temperature of the nozzle, hot glue might actually melt wire insulation. It's not a big deal with low voltages, I guess. The only thing that can happen is your circuit breaks. That's probably the worst. Now, if you do that with mains wires, please look out that you don't short the mains or don't short mains to something else. Because by accident it went okay with my thing, but I can imagine it's not completely safe. So just be warned. Another thing I didn't fix but simply took apart to see how it worked was a LED mains bulb, light bulb. Was a replacement for an incandescent bulb. So what you usually find in these bulbs, I guess, is some sort of supply, LEDs obviously, and some kind of regulator. For example, constant current regulator. Now this bulb was no exception, except the constant current chip was not what I expected. So in this one there was only a 3-pin SOT23 chip. And a friend of mine came up with a similar chip. I'm not sure if it's the same, but looking at the circuit it's pretty much the same. Looks the same, which was a BPS BP9918C chip, which has 3 pins and contains a 500 volt MOSFET. Now, how to do that with 3 pins, I wondered. I'll put a little schematic in the show notes and also maybe a link to the datasheet if I can find it. So one pin is connected through a sense resistor to ground, or what you can call ground. Another pin of the chip is connected through a ceramic capacitor to the same ground to supply the chip with power under switching. A little buffer. And another one was simply the MOSFET drain. So there was an LED strip with an inductor in series to prevent the current from turning sharp on and off. So I'll put a little schematic in the show notes. It's quite interesting how to do that with 3 pins. I never saw that. Next up, an LED strip. What else? Over here where I live, there's a cheap store. It's called an Action Store, and they have all kinds of stuff. They have food and clothes and everything, and also electronic gadgets. And sometimes I go there to take a look, and if electronic gadgets are cheap enough or interesting enough, I buy it to use it or take apart in this case. Now this LED strip was silicone coated. It had a nice diffusing effect and was not too expensive, so that's a win. That's one of these infrared remote controls, so you can select a certain effect for the LED strip. It was an RGB strip. So I was expecting some sort of smart LEDs or serial LED controllers to be inside, one per LED. And that was something like that, except it was a little bit different than what I expected. Usually, or at least what I saw, these LED controllers, for example WS2811, with 3 PWM outputs and serial signal going in, serial signal going out. The logic supply and the LED supply is both maximum 5 volts, I think. But with this chip, it was a GRE-LED Electronic Limited SM16703B chip. From what I could see in the datasheet, it was pretty much pin compatible with WS2811. Also had the same protocol, except the logic voltage was still 5 volt max, but the LED voltage was 24 volts max, 5 to 24 volts. And that's convenient, so instead of basically one LED, you can connect a whole LED, a whole series circuit of LEDs to one PWM output, and that's exactly what they did in this strip. So using this chip or a similar chip, you can save on controllers basically. If resolution is not the biggest issue, you can do it like this and connect multiple LEDs to one PWM output. So one little thing I never saw before. Now, while trying to figure out how basically while reverse engineering the strip, there was a white coated LED strip, the white coated flexible PCB, and I find it very hard to see how traces run on a white PCB. So what I usually do is have a little glass fiber brush that you can use to scrape the solder mask off the PCB. So this thing basically costs nothing, and it's very convenient to use it a couple of times to reverse engineer PCBs and also to clean it if you need to rework a PCB. So if you don't have it, maybe pick one up and see how it works. And the last thing I took a look at was a Christmas light decoration. It was a long string of incandescent lights with a little controller box, and you could select different effects for the lights to play. One of the effects was a very smooth fade in, fade out effect. It was so ridiculously smooth that you couldn't see, or at least I couldn't see, transitions between different intensities. Super smooth. So I took a look at the voltage going through the lamps to see what it was actually doing, how the controller worked, or what the controller was doing. I found out it was a 100 Hz PWM signal, and I found out it was a 7-bit PWM signal. Now, 100 Hz, you can do that with incandescent lights because it's basically a glowing wire. It takes time for the wire to start glowing, and it takes time for the wire to stop glowing. So 100 Hz, you won't see that flickering at all. And one smart thing I found what they were doing was, now let's say you have a 7-bit PWM, the lowest intensity, other than 0 would be to have 1 bit high and 127 bit low. So what they did in this case was, for 2 consecutive PWM cycles, they would output first cycle a 1, so 1 bit high and 127 bit low, and for the next cycle they wouldn't output any bits high. And in effect you have a 14-bit PWM now, so that's quite a high resolution. You can do that again with incandescent lights because of the averaging effect, let's say that, because it's so slow. So it's quite a clever trick I have found. I never saw that before. Oh, maybe this is interesting. For poking at wires, in this case the Christmas light decoration, there were 2 wires. I didn't want to take them apart. It was a perfectly good Christmas decoration. So what I did was take 2 pins, simple pins, stick them in the wire, so through the isolation and through the wire core, and connected crocodile clips to the pin. So this is essentially a vampire tap. You can poke inside a wire, essentially without leaving any traces. So worked quite well in this case. Maybe it's a tip for you. Next up, something that has nothing to do with electronics or software or mechanical stuff, but has to do with efficiency of the body, I guess. Now, a while ago I had a talk with a friend of mine, and we were wondering how efficient the body was in converting food energy to, let's say, mechanical energy by pushing or pulling something. And it turned out to be about 20%. So the next question you can ask is, how useful is it to do exercise of some sort in order to lose body weight, to burn fat, essentially? And when we were talking about that, we did some back-of-the-envelope calculation, and it turned out to be a ridiculous result. So I didn't believe it, to be honest, at that point. Now we did the calculations again with actual better models, let's say that, and it's still amazing. So we're going to go into that a little bit. There's a lot of numbers. I'm not going to bore you with that. It doesn't make for good podcasting, I think. So just going to give you a summary. Now, as a model exercise to calculate energy expenditure of, I'm going to use a deadlift, which is essentially pulling a barbell from the floor to a standing position. That's all. So I'm going to include a link to a paper from a John Garhammer who did exactly that. He gave a mathematical model giving a certain weight and a certain body weight and a certain height to calculate energy expenditure of needed to perform that lift. And let's say you are a 100 kilogram heavy person and you lift a 100 kilogram weight from a crouching position to a standing position. Now for me that's about 60 centimeters difference. You can calculate quite easily how much energy it takes to lift the weight itself. And furthermore, because your body goes from a crouching position at the start to a standing position at the top, you're effectively lifting your own center of mass a certain height. It's not as high as a barbell, but you about half as high. So if you do the math, the total energy in this case would be 931 joule. So that's about 1 kilojoule. And that is 0.22 kilocalories. Where I think 1 kilocalorie is about 4.2 kilojoules, something like that. Just for reference, what is 1 joule in mechanical energy? Suppose you're sitting at a desk, typing, and you have a full can of Coke, or a beverage of your choice, and you lift a can of Coke from the table to your mouth. That movement is about 1 joule. So one deadlift with 100 kilos is about 1,000 times that. 1,000 times lifting a can of Coke from the desk to your mouth. Now, I said earlier, the body is about 20% efficient converting energy from food into mechanical energy. That means in order to output X mechanical energy, you need 5x of food intake, basically. So if you do the math, one lift of 100 kilos consumes about 1.1 kilocalorie of energy from food. Now, assuming you continue lifting, you do that continuously with 5 seconds in between lifts, and you do that for a long time, you burn about 792, let's say 800 kilocalories per hour, which is pretty much the same as running. So you can compare that to running, lifting a weight every 5 seconds. Now, for how well this applies to actually burning fat, you can consider that fat has about 9 kilocalories per gram, so it's quite energy dense. And to burn 1 gram of fat, you would need 8 such deadlifts, 8 pulls. And even more ridiculously, to burn 1 kilo of fat, you would need more than 8,000 deadlifts. To put it in reference, that's more than 11 hours non-stop lifting, 5 seconds per lift. That's ridiculously long. And similarly, to burn a Kit Kat bar, which is about 230 kilocalories, you would need 200 plus deadlifts, which is pretty much 17 minutes non-stop. So if you think to yourself you exercise for 5 minutes, whether it's running or lifting weights, and you think to yourself, oh, I did a lot of work, I deserve a pizza or something like that, you better think again, because you're fooling yourself. So I find it quite interesting. So what did we learn? To lose weight, don't just do a lot of exercise, simply eat less, that's it. Or eat less crap, in my case. So, onto stuff that I actually made from scratch, or started to make from scratch. The first thing is a sort of weird thing, very simple. It is a wall socket thing, it's a main appliance. You can plug it in the wall, and you can plug a main appliance into the thing. So it has a plug and a socket. And what it does is convert essentially a single pole switch to a double pole switch, so it has 2 relays and a fuse, I think, that's it. For example, if you plug the thing into a wall, and the wall only has a single pole switch, so it interrupts either the line or the neutral wire. And since sockets here in the Netherlands are symmetrical, you don't know which is which. Now, if you want to have your appliance disconnected from both mains, from both line and neutral, you would need such a thing, or you would like such a thing, to turn a single pole switch in the wall, essentially, or in your electrical outlet thing, to a double pole switch. So for safety, essentially. So you can be sure that if you want to disconnect something, if you want to turn off something, that it's really turned off. It's not connected in any ways to a line. That's the whole thing. So yeah, might be useful or not. I made it for the Hackalot hackerspace in Eindhoven, so we'll see if it's used or not. It was nice to make anyway. It's the simplest project ever. Next thing I'm doing is also for the Probably for the Hacklot Hackerspace here in Eindhoven, maybe also for Awesome Space in Utrecht, or maybe at home, I don't know. Maybe I build a few, maybe I build 0. But I may have talked about this a little bit next episode, or the previous episode. It's not that interesting. It's a LED decoration, again. It is like a ball, a 5 centimeter diameter ball, plastic ball with spikes, like icicles, transparent icicles sticking out. And the original thing, I bought it at a cheapo store nearby. It had LEDs and a very quite boring effect. And it had, I think, 14 of these spikes coming out. So what I did was take a plastic ball, bought it at a DIY store online somewhere, drilled holes in it, and what I'm going to do is add more icicles, I think 26 or 28 or something like that. So first of all, that's more is better, and use a better effect behind it. So to do that, so that's the mechanical stuff. To do that, I made an electronic board. It's a very small LED driver. Maybe I told about that in the last episode. Whatever, you'll hear it twice, no big deal. A very small board, a 32 channel LED driver. So for this I used a small microcontroller and 2 NXP PCA 9745BTWJ, if you're playing at home, LED drivers which are constant current 16 channel SPI devices basically. And it works quite well. It's a very small PCB, so you can embed it into stuff and make it do nice light stuff. A little funny thing. Recently I moved from home office to an actual office outside of the house to do work. And there's always a little bit of room planning involved. What goes where do you put this cupboard, and where do you put your desk, and does everything fit? Now, what I did last time, and it worked quite well, is to use an actual electronics layout, a PCB layout program. I use KiCad for everything I do here, so I use that to lay out your room. And instead of a PCB outline, I make a room outline. And instead of electrical components, I draw footprints with a scaled down version of a cupboard or a desk or whatever. So that works quite well. You can rotate it and pan it and see if everything works out. So that's my way of doing interior decoration, if you will. Maybe a tip for you. The last thing I made, successfully I might add, was a variable resistor, a big variable resistor. So it's a metal box I made, with a laser cut front and back panel. You have 2 4mm banana sockets at the front, essentially connected to a rheostat. I think it's called a rheostat. I'm not sure if a rheostat is different from a big potentiometer. This is a big ass potentiometer from 0 to 25 ohms, and it gets hot, and it's expensive and big. That's it. There's also a fan at the back of the enclosure, and a switch at the front of the enclosure, enabling the fan, or turning on the fan. Now, one thing I should remember is that real components are not perfect, so this is not just a resistor, it's also an inductor, because it's a wire-wound device, and it's essentially a coil. So just for fun, I calculated or guesstimated the inductance of the whole thing by the dimensions of the coil, and I calculated about 28 microhenry. Afterwards I measured it, and it was 30 microhenry, so that was pretty much spot on. So it's not a big deal, but I should remember, hopefully, that when I'm using this thing, in worst case, adding 30 microhenry to your circuits, you're not just adding resistance, you're also adding inductance. So in effect, you're adding about 30 meters of mains wire. Mains wire is about 1 microhenry per meter, so I should remember that stuff. One flaw with this thing was pointed out to me by a friend. In this case, the fan is completely separate from the resistance, or from the load. So if the load gets hot, you manually have to turn on the fan. Or you shouldn't forget to turn on the fan if the load gets hot, rather. So a friend of mine came up with an idea where when turning on the fan, you would also turn on a relay, and the relay would switch in the resistance basically. So if the fan was turned off, the resistance was infinite and you couldn't produce any heat in there. So that was a quite brilliant idea. Thank you very much for that. And I'll probably not implement it because it's too much work. So there. So that was it essentially. Usually at the back of the podcast there are some upcoming events, locally or internationally, but to be honest I couldn't be bothered to look for events. So I'm not going anywhere techie or software or electronics related. I'm going to do some other stuff. But I hope you have a good time, and hopefully until the next episode, I hope it's a little bit sooner than 3 or 4 months away from now. And I think it will be, because I have some upcoming stuff that should be quite interesting. So that was all for now. For more information, links and previous episodes, visit podcast.cba.si. Stay tuned, thanks for listening, and goodbye.